now I'll kind of digress a bit, and let's look at some circuits made using switches, capacitors and resistors, just the three of these, but they might not be directly used in data converters as such, but you will find them very powerful and commonly used in radio receivers. And to motivate the first circuit, let's revisit sampling. We already know that when I sample a signal at Fs, at the input, if I have any signal of the form k times Fs plus or minus Fin, what will happen after sampling at Fs? Hopefully everyone is familiar that this aliases back to Fin. And with respect to ADCs, where we kind of look at the output sample here and then digitize it, this is a bad news, because spurious signals or noise from all of these frequencies can potentially alias back to my desired frequency range and can mess you up. But always remember, when we say something is not great or not good, it is all with respect to that situation and that context. It might actually be beneficial somewhere else. Same is true in real life also. Okay. So now can you tell me, can you think of a situation wherein this frequency translation can be used or might be needed? If I have, let us say, Fs plus Fin, looks like I get a Fin. Yeah, so correct. So I'm sure everyone is hitting at it. As you know, I mean, when we transmit a signal, you take a signal that is centered around DC. This could be what you speak, audio, your web page, whatever, and you upconvert it around a carrier frequency of naught and transmit it. When you receive the signal, the first job is you do this, and now you see that if I have a signal like this, I sample at Fs, I get back at Fin. So this mere sampling operation kind of helps you in doing this down conversion. And this kind of operations is called mixing, because it mixes the frequency. So circuits that can do this frequency translations are called mixers. And since we are doing this operation just by using simple switch, it's called passive mixers or sampling mixers. So it is the same circuit that we know. I take the input, sample it, let's say I have a capacitor at the output. So here, if the input is centered around a frequency, say FLO, again LO stands for local oscillator, that's the jargon used in comms, communications. So let's say the signal is this is V in. If I sample at LO, the output essentially falls back to DC. And let's say this strength is A0 and this is B0. So this ratio B0 by A0 is what we define as the conversion gain. So in practice, we make slight modification to this. So instead of having just one branch here that is tracking the input in one clock phase alone, we typically have two of them. Let's say it's phi 1 and phi 2 feeding the same signal. So again, the clock phases are same as before. This is, let us say, phi 1 and phi 2. And in mixers, we don't call it phi 1, phi 2. We usually denote them as phi 0 and phi 180. Just to denote that this guy is 180 degree phase shifted from the first clock. Because remember, one clock period is 360 degrees. This is half clock period away, corresponds to a phase of 180 degrees. So here also I'll change it, just a notational change. So here the first branch tracks the input while the second branch holds, and vice versa. Okay? And as you know, 0 and 180 degrees are essentially inverted versions. If you have a sine wave, 0 degree and 180 degree are sine inversions. So the thought process is, if I do this, I'll be able to get a differential output like this. Is that fine? So again, another reason is, again, if I had one branch, I get some conversion gain. Now I am using two branches and getting an output differentially. What do you expect the conversion gain to be? Double, right? I will give it as a problem, you can work out, but that's what happens. So again, you come up with something new, you first give it a name. So this is called single balance mixer. It's called a balance mixer because the output is differential. So we have differential thing. Input is single-ended. So yeah, single balance mixer. So here we are having a circuit where there are two parts. Each of the parts is tracking the input for 1/2 of the clock period. But it turns out you don't have to stop with two parts. In general, you can have n of these in parallel, and make sure each of these n branches tracks the input for 1/n of the clock period. So let us say from 0 to ts by n, the first branch tracks. From ts by n to 2 times ts by n, the second branch tracks, and so on. This also you can do it, and the motivation to do this is the following. If I look at the conversion gain here, so loosely speaking, it should depend on the strength of the sinusoid at FLO in this mixing sequence. Because again, loosely speaking, what we are doing, we are taking the input, multiplying with a square wave. Now we know square wave contains multiple sinusoidal frequencies. You are interested in down conversion from the fundamental frequency FLO. So whatever is the strength of the sinusoid at FLO in this sequence should determine the conversion gain. Is that fine? And again, you can work out, if I have a larger value of n and have multiple parts, the conversion gain actually increases. The intuition is because if you have larger and larger n, right, the clocks will look like this. If you keep increasing n, the clock pulses will become narrow and narrow. It will kind of mimic an impulsive sampling in that case. Because ideally you want an impulse sampling, but in practice you can't do, so that's why you do this square wave thingy. Right? If you find, you'll find that the fundamental in this impulse will be much higher than the fundamental in a square wave. That's all. If you look at the Fourier series component, the fundamental strength here will be smaller than the fundamental here. And if you have n of them, this is better. So this is what we do, but of course in practice, having a large n is not possible because you can't generate such narrow clock pulses. So the practical choice, common choice, is to have n as 4. So what we'll have is this. I'll have 4 clocks now. And if I have 4 clocks, what will be the duty cycle of the 4 clocks? 1 by 4, 25%. So the clocks will look like this. This is one clock. The second clock is non-overlapping like this. Third clock, fourth clock, and then it will keep repeating. So if I denote this as phase phi 0, what do you think is the phase of this clock? 90 degrees, because the time difference is Ts by 4. Ts is 360. So 360 by 4. And the next clock is 180. So we'll have essentially 4 parts like this. So there is another reason why 4 is chosen, because of the following. So how many of you here know IQ modulation? IQ meaning IQ. We heard? Okay. Okay. So if you don't know, I will improve your IQ today. So again, everyone knows when you are transmitting a signal, what you do, you take some signal x of t, multiply with a carrier frequency to upconvert it, and what is the mathematical operation to model this frequency translation? I have x of t, I want to shift it to a frequency multiplication with, if I multiply with the cos, then frequency gets shifted around that frequency. This is fine. Of course, in practice, we don't multiply with cos, we multiply with a square wave, let us say phase phi 0, because a square wave contains multiple sinusoids, that does the job. But for analysis, we still use it because this is easier. Now, this is the transmitted signal. Let us say you receive it, and after you receive, you have to down convert. How do you down convert? You again have to multiply with the same thing. So let us say you do this. So now I have cos square FLO. Cos square x is what? So it's 1 by 2 plus, what is the other term? No, it's cos only. Okay. Oh man, everyone forgot trigonometry. So now you see I got back the signal here, and this is shifted to a much higher frequency, don't worry. Right? Again, the reason we are getting is, reason we are able to get the signal back is cos square theta is 1 plus cos 2 theta by 2. This cos square x has a DC term, and that's why you are able to get back the signal. Right? So that's when kind of people, engineers kind of remembered that in 7th standard, hey, we also learned another trigonometric identity, and which was sin theta times cos theta. What is this? Nice. Right? And this term does not have a DC component. So that's when people thought, so what if I take x1, multiply with cos 2 pi FLOT, take second signal x2, multiply with sine of the same frequency. I add it up and send it. Of course, now if I look at it, looks like I'll not be able to differentiate x1, x2. This is what you receive. Now let us say I want to get back only x1. Remember that here we were able to get back x because cos square x had a DC term, whereas sine times cos does not have a DC term. So what do you suggest we do to get x1 here? If you do this, I get back only x1. We will not get x2 because sine times cos does not have a DC term. To get x2, what do? That will give you. So this way you can actually pack in 2 times the more information within the same resources I have. Right? Of course, in practice, again, we don't multiply with cos and sine. We'll multiply with the square wave with phase 0. And sine, what is the phase? So this is what is called as in phase and quadrature. In phase for 0 degree, quadrature 90 degree. Again, appreciate this because this is all possible because cos square does not contain, cos square contains a DC, this one does not contain. So if someone asks you next time what is the use of learning trigonometry, say that if engineers didn't know about trigonometry, your internet speed will be down by a factor of 2. That's actually it. If let us say you didn't know about trigonometry when you are designing a radio receiver, or let's say the people who are doing it, this might not happen. Sine of, let's not worry about, see, the point is the phase difference between the two is 90 degrees. So yeah, this is done, and now if you see, if I have 4 parts here, I'm automatically getting 90 degree thing. So in the earlier case, I had 0 and 180 and I called this as the differential output, right? Now with 0 and 180 I will be getting the in-phase part, correct? I multiply with a term which has 90 degree phase shift and a 180 degree phase shift from 90, that is the differential version. This will give me the quadrature. Okay. So now all you have to do in principle is, take Vi, give it to an ADC, quadrature, give it to an ADC, and in principle a skeletal receiver is kind of done. But this is no longer this is nowhere close to a fully functioning practical receiver because there are other practical issues, and one such issues what I'll explain next. But this is okay. I'm not planning to, this is not supposed to be a comprehensive explanation on passive mixers, but I just wanted to give a brief glimpse as to what are the different things you can do just with these two fellows. So again, another problem we have while receiving a signal is this. So let's say you are receiving a signal. Let's say this is the signal you want around FLO. Now of course your receiver is not receiving just this. It is going to receive all kinds of other junk signal. So you might be taking the telephonic interview of your life, and your neighbors and people in your like next rooms, they'll be chatting with their boyfriends and girlfriends, and they'll be blasting lots of power. Well, you are trying to receive a small signal, and obviously you don't want to receive those signals. You want to only receive your signal. So before you down convert, what should you do? First select the required this, so you have a filter. And what kind of filter? It's a bandpass filter. And again, it turns out in practice the bandwidth of the signal you receive is much smaller. It's few hundreds of kilohertz or few tens of megahertz, depends on the standard. But the center frequency will be of the order of several gigahertz, again depends on the standard. So in practice, we want a bandpass filter, but the bandwidth is very narrow. This is what you want, fine. And also remember that it is not like as though you will be transmitting and receiving around this constant frequency. Depending on the availability in the spectrum, you will keep hopping to or switching to different carrier frequencies. So it is not enough if I have a fixed bandpass filter. I should also be able to change the center frequency of the bandpass filter. So I'll say we need also a programmability here. Now, of course, you guys know to make bandpass filter, the easy choice is to have some kind of an LC. But it turns out on chip having an inductor takes hell lot of area. So unless your inductor value is few hundreds of picohenry, this is not practically viable. So as of now, the way we do it is this filtering is not done on chip. We have an off chip filter, and that is not done using transistors. It is done using MEMS filters. It's called surface acoustic wave or bulk acoustic wave filters. So you'll have an off chip component, and this has a fixed center frequency. So you actually will have a bunch of them for different center frequencies, and depending on what center frequency you want, you select the required one and give it to your chip. Now, of course, the looks like this is kind of taking up a lot of area. So that's where the motivation is to find some possible solution to have an on-chip programmable narrow bandpass filter. Oh, the center frequency should be changeable, right? It's not, that's because you don't always transmit and receive in one particular center frequency. The channel frequency keeps changing depending on the availability of the spectrum, right? So again, one line of thought for that is this. So we are kind of convinced that having a narrow bandpass filter on chip is not possible, but we can make narrow low pass filters. right? What is the simplest low pass filter, you know? An RC filter. So if I have an R and C, I can choose a large R, large C. I should be able to have something that has a narrow, you know, like chop. Okay. But I don't want to do filtering around DC. What I want is, I want to filter my signal around FLO. I want to have the same filtering to happen here. This is what I want. I want to do the same filtering around a frequency FLO, but looks like I can do the filtering nicely around DC. So what do you propose we can do? Huh? If you can somehow down convert this to 0, then I can use low pass filter. That idea fine? And I mean, I down convert, filter it, but that's not done. What should I do? Again, send it back to the same frequency. It's like you go to your, you know, grandma's house, have a lot of nice food, come back to your house, right? So, so how do you mathematically model this down conversion? Huh? You multiply with, yeah, cos or sine. Let's take cos. This will down convert. Now you do low pass filtering, and then you up convert. Sorry, again do the same thing. Right. Now, of course, in practice, it is difficult to multiply with cos. So what you do? Yeah, change it to a square wave, because thanks to Fourier, we know that square wave contains multiple sinusoids. So multiplication with square wave is trivial. Okay. So this part is fine, right? I can have an on-chip low-pass filter which is having a narrow bandwidth. Yes. But I want to do this filtering around another frequency FLO. So the idea is I first down convert to DC. Clear? I down convert to DC, filter it around DC, push it back to its old frequency. That doesn't have a narrow bandwidth actually. Right? That will have very shallow response. You can actually check it. You will basically do something like this, tutor RC and CR, right? Yeah, this will not be, I mean, basically it turns out there is a technical term, we call it quality factor. That is the center frequency by bandwidth. Yeah, this will be much smaller for this. The best bet is to have an LC. That is the best you can have. So yeah, so now we'll replace this with multiplication with square wave. And how do you multiply with a square wave? I want to multiply with a square wave going from 0 to 1. What is the simplest circuit that can do this? Yeah, if I want to multiply with 1, I'll connect the input directly. If I want to multiply with 0, no, I cannot open. I want to multiply with 0. See, this signal must be equal to V in when the clock is high. It should be 0 when the clock is low. I should have another switch. So I'll call it phi 0 and let's say phi 180. So same thing will happen at the output side. Phi 180.
So if you are down converting and then filtering and then again up converting, then I will again down convert.
Yeah, it depends. So sometimes, yeah, we'll come to that. So let us say you want to have only band pass filter, you can do this actually. We'll come to that. So hold that thought. We'll come to that. Okay. It's a good question, but we'll answer it. So if I do this, in principle, I should be able to get a frequency response around FLO like this. It's basically the RC's frequency response shifted around FLO, and the single-sided bandwidth will be 1 by 2 pi RC. Same RC bandwidth. Okay. But yeah, I mean, this will be the case if you had multiplied with a pure cos, but you are multiplying with a sine wave going from 0. Sorry, multiplying the square wave going from 0 to 1. So square wave contains how many sinusoids? Infinite number of sinusoids. So what do you expect the frequency response to be? Since you are multiplying with multiple sinusoids, the same thing will get repeated around the harmonics of twice, thrice, whatever, right? You'll have copies of this. I mean, and also, is there a DC term here? Going from 0 to 1, DC is there, so you'll also have the same thing repeated at DC. So this is one problem, but again, the hope is you can have a shallow filter and filter the rest of it. So this is basically when I apply a sinusoid at F1 and then see what is the strength of the sinusoid at F1 in the output. So so in practice we make one minor change to the circuit. So I will not explain in detail, I will just qualitatively explain. So here if you see during the clock phase phi 0, I am charging the capacitor with something. In the other phase phi 180, looks like I am kind of losing that information, right? So at least qualitatively speaking, it makes sense that with respect to having a larger gain, I probably don't discharge this and let the capacitor hold the information that you put in earlier. I am not going to details, but at least hopefully logically it should make sense that if I pull this to ground, I am losing information. So within quotes the gain will be smaller. Whereas if I don't let it discharge, the capacitor is holding the same voltage. So hopefully the gain is higher. Again, let's not go into details, but this is fine. So in practice we don't have the switch. But if you remove the switch, the earlier one and this one, they are completely different. Okay? And one fundamental difference is this. Here, if you actually see, let's say remove this. During the clock phase phi 0, we are connecting the input like this. The capacitor sees a resistor in series with it. So what is the RC bandwidth in the clock phase phi 0? If you have a simple RC like this, what is the bandwidth? Fine. Now in clock phase phi 180, I am basically connecting it. The capacitor is still connected to the same resistor. What is the bandwidth? So what do you think is the overall bandwidth? Overall bandwidth is also same. That's what we also get here. Fine. But now if you see here, in the clock phase phi 0, same thing. What is the bandwidth? Phi 0, let me draw, it's 1 by 2 pi RC. In phase phi 180, this is open. We are seeing an open circuit. What is the resistance connected across the capacitor? Infinite, it's open. What is the bandwidth? 0. So what do you think will be the overall bandwidth? Take a guess. In one phase it is 1 by 2 pi RC. Other phase it's 0. What? You think very convoluted way. What is the logical thing?
1 by pi RC.
Half of it, 4 pi RC. I mean, at least logically it might be average of the two. Okay. Again, you can actually rigorously prove it. It's not that difficult, but let's not spend time on it. So the bandwidth now will actually shrink. And remember, we were trying to make bandpass filters with narrow bandwidth. So this is a good news or bad news? Okay. So actually, if you look at the this circuit's response, it might be narrow, and the gain is expected to be higher. So the bandwidth will be 1 by 4 pi RC. This is another reason why we might.
Won't the information get stacked up because at 5 is close?
Yeah, that's what you want to do, right? Filtering is you kind of stack up based on the previous information, right? This is fine. So yeah, so this is one way to get narrow bandpass filter. And here, if I were to change the center frequency of this filter, What will I change? Center frequency. What is center frequency here? No, from here what is the center frequency of the filter? FLO. If I were to change the center frequency, what do I do? Change the frequency of these clocks. I just take and change the frequency of the clock. The bandwidth the center frequency can be actually programmed to anything you want. Okay. So this is one nice way to have a programmable on-chip bandpass filter. But again, this has a bunch of issues, and one issue is this. See, here when I plotted the frequency response, what I have done is I have applied a sinusoid at f1, found out what is the strength of the sinusoid at f1 in the output. That's what is giving me this plot. But remember that we are doing lot of sampling and lot of switches are happening. So if I find that I see a sinusoid at f1 in the output, it need not have come just from f1. It could have come from any frequency of the form k times fs plus or minus f1. The same old aliasing issues. Okay. So just like how we plotted a transfer function that told if I apply f1 at the input, how much of f1 I get at the output, you will have multiple transfer functions that will define if I apply a tone at fs plus f1, how much will come at f1, 2 times fs plus f1, how much will come at f1, and so on. Bottom line, you will have a lot of aliasing. Okay. Now if you want to, let us say, reduce the effect of aliasing, do you think I should have a larger fs is FLO here, do you think I should have a larger FLO or a smaller FLO? If I want to reduce aliasing, should I be sampling faster or slower? Your statement is correct, but the inference is wrong. Yeah?
So that we can spread out the.
Remember, if I make it infinity, what happens? Aliasing is coming from infinity large frequencies, it's okay. You sample it faster, you are preventing aliasing. Okay. So, but now if you keep increasing the frequency, the switches will be difficult to design. So that begs the question: is it possible for me to cheat by having only a circuit, let us say, that samples at FLO, but to the outside world I should make it look like we are sampling at 2 FLO. So basically I want to also sample these points. As of now I have one circuit. I am giving a clock phi of t at FLO. That is basically taking these cross samples. But let us say I also want to take these points. Yeah, again, the observation stems from the fact that this clock period, this time period is TLO. What can you say about this time period? That is also TLO. So which means I can get these samples by using an identical copy of the same circuit. But what should be different? Yeah, I should be sampling with a slight timing offset, right? So I will take another copy of this, feed a clock which is delayed by half clock sync, and then if I add the outputs here, to the outside world it will look like things are happening at faster rate. Fine. Again, we will return to this concept later, but the idea should not be that difficult to understand. No, you don't. Let's say, designing circuits at high frequencies is tricky. Okay? So now we'll try to do the same thing. So I'll have this. I'll make a copy of this. The clocks to the second circuit should be delayed by 180 degrees, right? Shifting it by TLO by 2. TLO corresponds to 360 degree phase. TLO by 2 is 180 degree. So this will become 180. So this will become 180. And this will become 0. No, it's as of now, let's say you do it by 2 times. 180, right? Again, like he's pointing out, I mean, we don't necessarily have to stop at 2x. If you want to make it 10x, you can have 10 of them, have each of them sampling with TS by 10 offset. Let's start with 2x, that's simple to see, right? That's all. So I have 2 of them, and finally I have to go and add these 2 fellows. Get this. If I do this, hopefully the number of aliasing that happens, I mean earlier let us say there were 1000 frequencies that were aliasing. Now if I do this, how many frequencies do you think will alias? I mean less, but can you give me a factor? Huh? We are increasing the sampling frequency by 2x. So the number of things that can alias back will half, right? Cool. But here is where the circuit nicely starts to beautify itself. So here, if you see, let me call this as VO1, this as VO2. In the clock phase phi 0, what is the input to this part of the summer? In phi 0, what is the signal appearing here? V01. What is the signal appearing here in clock phase phi 0? It's grounded, that is 0. So what is the output in phi 0? Similarly in phi 180, if I look at it, in phi 180 this input is 0. So phi 180, the output is VO2. So now looks like this guy is not doing anything. It is not actually summing up 2 signals, because at any given point of time only one of the signals is non-zero. Okay, and this is happening because the 2 clocks are non-overlapping. At a given time we just have one of the branches active, the other branch is not active. Okay, so now how do you think I can simplify this? Directly? Yeah, so now all I have to do is this. During the phase phi 0, my output should be VO1. During phi 180, it should be VO2. So all I will do is this. I will remove these completely. In phi 0, VO1, phi 180, VO2. So again, you don't necessarily have to stop with 2 of these parts, as I mentioned. You can have general n, and again in practice we choose n to be 4 because of similar reasons. So when I do that, what I'll get is this. I'll try to extend it for 4 clock phases. Four clock phases. So again the same thing, the clock should be non-overlapping. That is the crucial thing. That is what is making this fact of eliminating the summer possible. We don't need to do the summing operation because at any given instant only one of the branches is non-zero, right? So here also if you have 4 parts, I should have something like this. So again the clock phases I will change. So I already have 0, 180. I'll add 90 and 270. Okay. So now again you can do further simplification. So let me move it to the next page. So here if you notice, the resistor is basically present in all 4 branches. A resistor is a memoryless element. So what can I do? Instead of 4, I can basically push the resistors out of this branch and then share the resistor among all 4 branches. Now remember, I can't do this with the capacitor because capacitor is holding some previous information, so it is unique to each of the branches, but the resistor is common, so we can actually remove individual resistors. Okay. And then have a common resistor at the output here.
So all the resistors aren't active at the same time.
Correct. Yeah, exactly. That is good. That's also a point, right? Because at a given point, only one of the branches is active. This is happening because the clocks are assumed to be non-overlapping. So this is in practice called the N-path filter. Again, this is a 4-path filter, and generic extension is N-path filters. So in practice, there is another common variant. I will just show that and end the class today. See here, actually let me label the outputs properly. This is, let us say, VO3, VO4. Now tell me, this is the output. My output is during clock phase 50, output is connected to VO1. During clock phase 590, output is connected to VO3, 5180 VO2, 270 VO4, and so on. That's what we want at the output. Now can you stare at the circuit and tell me, is there some other node where I can get the same information? That is, during one clock phase, I should get VO1, another clock phase VO2, and so on. I can't understand this. You should tell me with some more description. Right side of the resistor. Now you see this point, right? That is basically doing the same thing during, when this switch is, when the right side switch is active, this is also active. So VO1 is connected here. During the second clock phase, this is connected here, and so on. So I don't necessarily have to have the output side switches. Okay. So what is my output node now? This guy. Okay. Right. Again, this circuit and the previous one both have their own pros and cons, but with respect to simplicity, this one definitely wins. So now look at it. I apply a Vin here. At the output, I get a bandpass filtered output. So if I go and connect this to an antenna, I receive a signal that contains a lot of junk things also. If I look at this output, I have gotten a bandpass filtered action. So in principle, I would have been able to select the required channel at this point. And do you recognize this portion? This alone, do you recognize what it was doing? It was a sampling, but we just saw, right? It is also doing mixing operation. This part is a passive mixer that can basically down convert the signal. Oops. Yeah, this is a passive mixer which can down convert the signal from required carrier frequency to DC. So now you see I receive a signal here that is filtered here, and here it is down converted. So again, this is going to be my in phase. This will be my quadrature. So all I have to do now is take this guy, give it to an ADC. Take this guy, give it to an ADC. And you can, if you want, you can also reuse this as a sampling capacitor for the ADC. And then reasonably functioning radio receiver can be built. Okay. Again, in practice, this is not good enough because you have a whole bunch of issues, because the aliasing problem is still there, and also the filtering you get with this is kind of, the rejection is not that great because you still have an RC kind of thing. The out of band rejection of the filter is not that great, but yeah, this seems to be as of now the only way if you want to have an on-chip filter cum receiver.
Instead of the RC filter, if we place some kind of active filter initially when we started, and then we do that sampling modulation.
See, you can do it, right? I mean, I'm not saying this is a simpler thing. That's what people have been trying to make this better and better. The issue is, if you the beauty of this is there is no active element required. If you want to use op-amps, the op-amps need to run at high frequencies, so designing will be a challenge. But of course, people are doing it. So again, it's not, this is not meant to be a complete comprehensive explanation on mixers and N-path filters. Just want to show that just by using simple switch, resistor and a capacitor, you can actually build a radio receiver. So it's like, capacitor you see and you laugh at it, say, what are you are so simple. And then it goes and calls its friends, resistor and switch, comes back, and then now it's like, like a big thing. Okay. Cool.
Was this ever used at a time?
No, not yet. This idea of N-path filter is slightly more recent, right? And as I told, this still has a lot of issues. This is still in its infancy stage. So people are trying to address issues, and but there are a lot of issues, but still it looks very nice and very promising. We are still working on it. Okay, so we'll stop here and then we'll continue.